So yeah, percent composition was pretty easy, right? Well, you knew that wouldn't last long because we can use percent composition for still more things. Yes, indeedy, we can. Let's go back to where we were. Maybe we've seen this, maybe we haven't. Okay, let's take a look at the compound benzene. Benzene is a 6-membered carbon ring. It's C6H6. It's a flat ring with 6 sides. And we have acetylene. It's used in blowtorches for welding. Its formula is C2H2. Now, if you look at each of these, they are each 92.3% carbon and 7.7% hydrogen. Is there anything you notice about these two things that they have in common with each other besides the percent composition? Okay, so somebody's going to say, if this was the classroom, they're both made of carbon and hydrogen, right? And somebody is going to say the carbons and hydrogens are equal to each other in both of them, which is very correct. It's on the right track. And what happens with these guys is they have the same simplest formula. Each of them has 1 carbon to 1 hydrogen. So they have this mole ratio of 1 to 1 in both of them. You can reduce 6 to 6 to 1 to 1 and 2 to 2 to 1 to 1. Okay, so that simplest ratio for each one is C1H1, and that's what we're going to talk about right now. You're like, C1H1? Aren't you done talking about that? No. Okay, so this simplest whole number ratio of elements in a compound is called the empirical formula. Let me write empirical formula up here where you can actually see the word or words. Okay, so we're looking at empirical formula. It sounds horrible, but it's not too bad. And the empirical formula is the simplest whole number ratio of elements in a compound. You can't make this any simpler. You can't say C.5, H.5. Okay, anything with a 1, it's always going to be an empirical formula because you can't make a whole number smaller than that. Okay, now we're going to compare that with the two formulas that I gave you up here, C6H6 and C2H2. Those are both called molecular formulas. Okay, molecular formulas are right here. And the molecular formula is the true representation of elements in a compound. So if I take the empirical formula, C1H1, and I multiply each of the atoms by 2, I'm multiplying the subscripts, mind you, I get C2H2, and if I take that same empirical formula and I multiply it by 6, I get C6H6, which is the true formula, or the molecular formula for benzene and for acetylene. So molecular formulas are some whole number multiple of the empirical formula, which is not a definition, but if you want to remember what I said, I just said molecular formulas are whole number multiples of the empirical formula. So let's look at a couple of examples. Whoops. Again, I leave words off of things. So I've got a couple of columns here. If I have the molecular formula for C2H4, can I break that down into something simpler? Yes, I can. I can make it be C1H2. I just divided them in half. Once I've got a 1 as one of them, I can't do much else. How about water, H2O? Can that be made any simpler? No, because I've already got a 1, an understood 1, by the oxygen. So in this case, the molecular formula and the empirical formula are the same thing. In this case, they are not. How about over here? H2O2 is hydrogen peroxide. Can I lower these numbers? Can I make these numbers a smaller ratio? Yes, I can. I can have H1 and O1. You usually don't write those ones, they're understood, but for now I'm going to write them down. How about P2H5? Well, I could make it be P1 something, but it would be P1 H2.5. H2.5, 2.5 is not a whole number, so I can't do that. So with P2H5, again, the molecular and empirical formulas are the same thing because I cannot make it simpler and still use whole numbers. Now, here comes the tricky part, calculating these little darlings. I tend to use this chart. Why do I use this chart, you might ask? It was recommended to me a long, long time ago by somebody I taught with at a community college. And what you're going to do until you get comfortable doing this is you're going to fill this out at least with with a shortcut for these headings, but you're going to have a column for the element you're interested in, the number of grams of that element, the number of moles of that element, something called the mole ratio, which I'm going to explain, something called the formula ratio, and last of all, the simplest formula. So 1, 2, 3, 4, 5, 6 columns. If you get them right, one just leads right into the other one. And magically you have the empirical or simplest formula at the end. So let's see how this works. I'm going to find the, I want to find them, what did I just do? Oh, okay. I'm going to find the molecular formula of an element of a compound that is 11.1% hydrogen and 88.9% oxygen. So the first thing I'm going to do with that is I'm going to find the mass of each element instead of percentages. Okay. Sorry, what you're really trying to do here is find the molecular formula or the empirical formula. So we're finding the empirical formula for something which is 11.1% hydrogen, 88.9% oxygen. So what we're going to do is assume we have 100 grams of whatever this compound is. And if we have 100 grams of that compound, we have 11.1 grams of hydrogen and 88.9 grams of oxygen. All right, so you could have assumed 1,000 grams. Then you would have had 111 grams of hydrogen and 889 grams of oxygen, but why bother? Just assume 100 grams, make the percentages grams, and get on with things. So here we have our elements are H and O. Our grams are 11.1 and 88.9. Now I need to convert to moles. To convert grams to moles, what are you going to do? You're going to divide by the molar mass. Okay, so I'm going to try to do these in a column under here. We'll see how well that works. For hydrogen, I have 11.1 divided by 1 gram. That's going to give me 11.1 moles of hydrogen. And if I have oxygen, I have 88.9 grams divided by 16 grams per mole. That gives me 5.56 moles of oxygen. So having divided each number of grams by the molar mass, I'm going to put the answers in up here. 11.1 grams, 5.5, moles. It's getting late in the day. 5.56 moles. Okay, now I want the mole ratio. To get the mole ratio, I divide each number of moles by the smallest number of moles. Okay, so to go from moles to mole ratio, you're going to divide each number of moles by the smallest number of moles. So what's smaller up here, 5.56 or 11.1? Okay, let's look at hydrogen. 11.1 divided by 5.56, because 5.56 is smaller. Oxygen is 5.56 divided by itself. That gives me 1.00. This gives me 1.99 moles of hydrogen and moles of oxygen. Okay, 1.99, 1.00. Here, formula ratios, you want to make these numbers integers. It's easy to do in this case because 1.99 is extremely close to 2. 1.0 is 1. So 2 and 1. And the empirical formula then is 2 hydrogens, 2 on oxygen. So we're just taking these, the formula ratios, and making them the subscripts. Now, there's a little problem here. If you have a mole ratio that is something like 2.5 to 1.0, to get the formula ratio, you are not going to round this 2.5 up because you can get an exact number if you multiply each of them by 2. Whatever you do to one, you have to do to the other. That would give you 5 to 1. 5 to 2. Suppose you had 1.33 to 2.0. You wouldn't round that down. If you multiplied that by 3, you'd get 3.99, which is incredibly close to 4. We'd have to do the same thing here, multiply it by 3, and you would get 6. So if you have numbers that are something and a half, or close to something and a half, like 2.49, you'd multiply by 2. 1.51, multiply by 2. If you have something and a third, you'd multiply by 3, and that would get you awfully close to a whole number. So don't just go rounding these things off willy-nilly, because that just doesn't work. Let me see. There's a cat there, in case you're interested. Roger, you want to show them the cat? Hi, cat. I guess that's it for these. And we'll get on to molecular formula in a bit.